Okay, for this example, we are asked to determine the magnetic field intensity for a uniform line current that has some magnitude I that flows on the z-axis in the plus z direction. I'm going to stop my sharing and turn on my whiteboard cam, and we will get started. So we're asked, first I'm going to draw my coordinate system because that's what I always do. And what we're asked to do is find the magnetic field due to a uniform line current density. So I'm just going to like sort of scribble on this to denote that there is a current there also. It's pointing in the plus z direction. And I'm going to say that I, the vector, is going to be some amount I naught a hat z, give it a vector direction, like that. And I would like to find the magnetic field intensity, so that means H, everywhere. We can start by setting up a general form of the Biot-Savart law. So we're going to have that H is equal to the integral. I'm going to write from minus infinity to infinity because this is an infinitely long line current of I dl. So that's I naught a hat z dl cross a hat r. We're going to worry about that in a second. Divided by 4 pi big R squared. The reason I'm not worrying about a hat r right away is because there's a symmetry argument that I would like to make. Let's say that I choose, I'm going to move this because I need some space to talk about my symmetry argument. Let's say that I choose some differential length element up here, right? We'll make that dl. In fact, we'll make it a differential current element I dl. And let's look at let's look at it here at this observation point. It's going to have the unit vector from my differential current element to my observation point points in that direction, a hat r. And if I were to draw dl points that way, a hat r points that way, I'm going to get dl cross ar is going to have a, you can't see my right hand rule, but that's what I'm doing right here, putting my fingers along dl, folding them onto the direction of a hat r. My thumb points in the direction of the result, which is downward into the board. So I'm going to draw a little X, and that's going to be the H that I would get from that. I also am going to get, am I going to get anything else? No, I'm not. Why am I not going to get anything else? Because this exists on the axis. There's no other directions here. This a hat r has a radial component, rho, away from the z-axis, and it has a z component, but it doesn't have a phi component. And there's actually no way for it to have a phi component because of the radial symmetry. No matter where I put a hat r, it can't have a phi component because the direction is always measured directly from the z-axis, and it can't happen that way. So a hat r phi component equals 0. Important fact, good to know. Now, the second part of my symmetry argument is this. If I choose a second differential current element, I'm going to make it IDL prime, let's say. And I draw its A hat R when I cross the direction of my current vector with the A hat R component, well, I guess I don't even need this part, because what I'm really saying is that A hat R has a Z component and a phi component, a rho component, but Z cross Z is going to be 0 because parallel vectors cross products are always 0. So only the rho component counts. Same thing up here, only the rho component counts. The Z component of this other A hat R also doesn't count. So this is less of a different components of my current distribution's contribution canceling, and more of just the cross products not producing anything there. So cool. A hat Z cross the rho component of A hat R. So let's figure out what the rho component of A hat R is using similar triangles. The convention is that we use primed coordinates for the coordinates of integration and unprimed coordinates for our observation points. So P is going to be at rho, phi, and Z. And IDL is going to be at rho prime, phi prime, and Z prime. But since it's on the Z axis, the first two variables are just 0. 0, 0, Z prime. And if I want to know, I'm going to draw this at a little bit more of an angle so it's easier to draw the triangles. Let's draw P down here. This length is Z minus Z prime. And this length is rho. So my unit vector A hat R here is rho A hat rho plus no phi component, right? Plus Z minus Z prime A hat Z, all divided by the magnitude of all that.
Professor, could you move the camera a little bit to the right, please?
Oh, thank you. There we go. Rho squared plus Z minus Z prime squared. This is going to be another one of those triangle-based integral substitution situations, FYI. Where's a good place to write this? Down at the bottom, I suppose. So now my H integral becomes, substituting everything in, integral from minus infinity to infinity. DL here is just DZ. So that's going to be I naught. I'm going to write DZ. Then I have A hat Z cross only the rho component, right? Because Z cross Z produces a 0. A hat rho, like that. Then we have rho over square root of rho squared plus Z minus Z prime squared. That's the magnitude of the rho component of my unit vector. And then down here, in place of 4 pi r squared, I'm going to have 4 pi, this stuff in the square root squared. So rho squared plus Z minus Z prime quantity squared. like that. So I can actually absorb this little square root into there by making this go to the power of 3/2 and erasing the square root. That looks pretty familiar. We've seen it before. A lot of people like to move the dz out to the end, so I'm going to put rho over here and a dz over there. I believe we evaluated this integral last time by looking it up. But I'm going to make
Professor, quick question.
Yes.
Sorry. If that's 3/3 for the exponential, wouldn't that just be?
It's supposed to be a 2. Thanks.
Oh, my bad. No problem.
No, that was me writing a 3 when I should have written a 2. Okay, so I'm going to talk to you about how to do this integral substitution, and then we're still going to look up the answer. Here's what we do. Where can I write this? If we have this triangle that we've been dealing with, this is rho, this is z minus z prime. This is square root of rho squared plus z minus z prime squared. Let's take a look at this angle.
Could you move the camera up a little bit, please? Sorry.
Better? I know this is really difficult because maybe I just need to like stack my camera on top of more books. Anyway, let's name this an angle. Let's name it psi. Then I can write that rho divided by that square root stuff is cosine psi. And this z minus z prime part, I can write that z minus z prime is, I could actually do that in 2 different ways. I could write it as the stuff in the square root times sine of psi, right? Or I could write it as rho times tangent of psi. So by using this stuff and then taking a look at what the values are of psi that I would have to substitute in the bounds for my integral, I can write down rho over, I'm just going to write like hypotenuse here, hypotenuse cubed dz. I can write that instead as a function of this angle and then substitute in the bounds for the angle. That's how you do that type of integral substitution. If your integral came from a triangle, you can substitute in these triangle forms, and it's pretty easy to integrate your cosines, your sines, and your tangents. A lot more easy than to integrate stuff where you have polynomials under a square root. So give me a second. I didn't actually mark the page where I looked up the value of this integral, but I do know what the result is. I end up.
A quick question, Professor, for that square
Yes.
root, is that sine psi of rho tan psi, are those supposed to be over each other or multiplied to each other underneath that square root?
There are 2 options of the same answer. So neither of them are supposed to be, they're not operating on each other at all. So this thing is equal to this thing, right? And this square root has the rho squared plus the z minus z prime squared inside it, like that.
Oh, okay. So you can either evaluate the square root of that sine psi or just do rho tangent psi.
Right. And so what you would have to do here is Oh, and this is a dz prime that we're evaluating the integral over, not dz. Somebody should have corrected me on that. Anyway, what we need to be doing here is we need to express this angle psi in terms of dz prime. Like what is d psi in terms of dz prime? And you're going to end up with some more factors of this stuff. And they all work out in a nice way. So then the result, when you actually do that, all of this, I'm going to skip to the end rather than actually working out the integral in order to give you more time to do your example. Then you get that h works out to be I times rho, the position of your observation point. Oh, I'm sorry. Oh, I'm in the wrong place. You get I over 2 pi rho a hat phi. And that's it. The way this happens is that this cross product that we wrote down when we were writing down the whole integral thing, a hat z cross a hat rho gets you an a hat phi directed unit vector. So that's where that comes from. And when you evaluate the rest of the integral, you get this 1 over rho factor in the bottom. And I used I naught here, so that should be an I naught. So again, I don't object to you looking up the results of integrals. I do it literally all the time. I wanted to explain to you how to evaluate that integral in case you ever have to do that, or can't look it up or are not allowed to look it up or something like that. And now, in order to give you time to actually try this yourself, I'm going to stop recording and turn it over to you into your small groups.